Hey, good evening, everyone. It's a pleasure to have Suman Sadhukhan speaking to us today. So he's a postdoctoral researcher at University of Haifa. Before that, he was a PhD student at University at INRI RN. And before that, he was a student at Chennai Mathematical Institute. So he's interested in games on graphs and its applications to formal verification. So over to you, Suman.
Thanks, Suman, for the invitation, and I will be happy to present this work. And please free to interrupt me, and I'll be happy to answer whatever in the middle. But yeah, I still feel like there will be some technical problems, because I can't remove the screens. But let's see what happens. So today I'll talk about bidding games on graphs, which will probably be new to some of you at least. And there will be two parts of this talk. The first part I will talk about theory of one bidding games on graph, and in the second part I will talk about one application that we are proposing of, bidding games on graphs in general. So why games in verification? I don't think this community needs an introduction for this, but still, for the sake of completion, I'm just giving one. So we know when we have a system which interacts with an external environment, we are often asked to model the system in a way such that it satisfies some given condition. For example, for an elevator, users put buttons out from outside and press buttons, and we are asked to verify that if the door opens only if the lift has the correct level, or if we press emergency button, then the elevator should stop like this. And when we are given such a model, we want to verify that whether that model is correct, that satisfies this kind of condition. So there are several such examples, and we typically model them as a system environment interaction, where environment gives input to the system and system outputs reacts by giving some outputs. And this interaction goes on. And there are some specification that's written in some logical formula, for example, linear temporal logic. And we ask typically that whether there is some controller that actually tells the system to output, such that the controller and the system satisfies the specification that's also given. And we address typically this problem. We are interested in synthesizing such a controller, or see if in a given environment or system interaction and given specification, such a controller exists or not. And this problem we can model in a two-player game. So this is the problem that I mentioned, and we try to approach this problem by constructing a two-player zero-sum game, which models the interaction between the system and specification, system and environment. And the specifications, we encode it as winning condition, and then the problem of synthesizing such a controller reduces to whether in that game there to know that if there exists a winning strategy or not. If there is a winning strategy for the controller in that two-player game, then we say that there is a correct by design controller for the given specification. Now, this is where the two-player zero-sum games comes in formal verification community, and we take it from there. And so, for example, say this is a model of such an interaction, and the two-player for today's talk, say like Bart and Lisa, and they have their the ownership of some vertices in the interaction. That means that whenever there is a token that moves around in this graph, and whenever the token is Bart's vertex, he will only choose whatever the next vertex will be, and vice versa for Lisa. And typically, say Bart has an objective. In this example, he wants to reach this target vertex, and we want we ask that whether whatever Lisa does in this game can Bart actually reach the target vertex or not. So this is what reachability games have. And the token moves throughout the graph and gives us an possibly infinite execution of the game. And the winning condition, the reachability winning condition is a finite duration, but there could be other winning condition that we'll consider in future in the talk, which are bookie, parity, etc. And I'll introduce what they are whenever necessary. And this is a zero-sum game. Is every such infinite play has one winner. And the decision problem that we are interested in is that given such a game graph and a winning condition that are like this, and an initial configuration that is, for this example, just an initial vertex, we ask whether Bart has a winning strategy. So this is two-player zero-sum turn-based game. But in this talk, we remove the ownership of the game graph. Everything remains the same. That is, we instead of giving a priori ownership of the vertices, we give some budgets to these vertices. And at each turn, we call for an auction, and the players bids from whatever budget, within whatever budget they are given. And whoever wins the bid at a turn gets to move the token from there. And the game continues as it is, and we still study the winning condition that we study in the turn-based two-player zero-sum games. And the decision problem, we adjust the decision problem in the sense that now we have a initial configuration that includes both vertex and a given budget, and we ask that if Bart has a winning strategy for the given winning condition from that initial configuration. So this is what we call bidding games on graphs, and bidding games have been studied in literature, not from verification community, but from in other contexts, and we adapt the bidding mechanisms from those literature. And for example, these Richmond games, and I have cited a few papers, you can look into it. But as of yet, I have just explained how the turn-based changes to bidding mode of movement of token in the game graph. But I have to explicitly mention how the bidding works, and that's I'm going to do in this slide. So in each turn, both players simultaneously submit legal bids, and the higher bidder moves the token. But I have to still fix more parameters, namely who pays after a bidding occurs, where does the bid goes after a bidding, and what kind of bids we are talking about. And depending on this parameter, we can study different particular bidding games. For example, in the first prize version of the bidding games, the higher bidder pays. In the all play, both of them has to pay. And in the Richmond bidding, higher bidder pays to the other bidder, or I mean, first price Richmond bidding, higher bidder pays to the other bidder. And four-man bidding, there is a bank where the bidder, whoever needs to pay has to pay there. And bids can be continuous or discrete. Continuous means the bids can be arbitrarily small, and for discrete bidding, it looks like coins, so it has a fixed variability. So for today's talk, you don't have to remember all of these variants. I'll only talk about first price Richmond, but both continuous and discrete. So first price means the higher bidder pays, and Richmond means the higher bidder pays to the lower bidder. So throughout the game, the total bid remains the same. The total budget remains the same. So as I said, that this talk has two parts, theory and practice. So in the theory part, I will talk about theory of discrete first price Richmond discrete bidding games, and then I'll propose a somewhat practical application of first price Richmond continuous bidding game. But in the introductory part, I'll just briefly show you how the bidding games generally is, and then I'll move into the this part individually. So So consider this an example of game graph, and Bart has this target vertex, and the decision problem that is I mentioned before. And we can pose the problem in the way that how much initial budget Bart needs to win in this game. That is to reach in this vertex where there is a ice cream. Sorry, I can't show the pointers. So this is a technical problem. So let's see. So because we are talking about continuous bidding games here, the total budget is normalized to 1. So I'm asking that what budget is needed for Bart to win this game, and let's see with points. Let's see what if we give Bart some budget just more than 3/4. That means that Lisa has, because the total budget is 1, so Lisa has budget less than 1/4, and Bart can bid quarter, which Lisa cannot match because Lisa doesn't have that much budget, and Bart wins the bid here, the vertex where the token fits. So he gives the budget to Lisa because it's Richmond first prize, and he moves the token to the next vertex because his target is there. Now the budget new budget for Bart and Lisa is this 0.5 plus epsilon and 0.5 minus epsilon respectively, and there Bart bids again 0.5 plus epsilon because again Lisa cannot match this bid, and Bart wins the bid, and he moves the token to his target vertex. So Bart wins the game in this. So we saw here that if we give Bart a budget more than 3/4, he can easily win this game. But the question was, can he do better? That means that can he win the game still with a less budget? And the answer is yes, and I'll show how it is. So let's say we give budget more than 2/3. That means Lisa has budget something less than 1/3, and Bart bids 1/3. Of course, Lisa cannot match this bid and this budget and bid, and Bart wins the bidding here and moves the token in the next vertex. And here Bart bids 1/3 plus epsilon, where Lisa has now budget 2/3 minus epsilon. So Lisa can, depending on epsilon, Lisa can bid 1/3 more than 1/3 plus epsilon or less than 1/3 plus epsilon. Of course, if she bids less than 1/3 plus epsilon, that is less than what Bart has bid, then Bart wins the bid and moves the token as before. But if she indeed bids more than 1/3 plus epsilon, then of course Lisa will move the token to the first vertex because Lisa wants to defeat Bart, and their new budget becomes like this. So you can see that we started with Bart's budget as 2/3 plus epsilon, and now even though the token comes back to the first vertex, his budget has increased to 2/3 plus 2 epsilon. So he can do that forever, so that and eventually his budget will increase, will be more than 0.75, and then we can play the strategy that I showed before. So what it shows that if I give Bart more than 2/3 budget, that is 2/3 plus any epsilon, then he has a strategy so that he can eventually win the game. And of course, we can still ask that, can he do any better than 2/3? That is, can you do anything? Can you still win with less than 2/3? But the answer is no, and I'm not showing, but you have to believe me. You can believe me, and we can in fact show that if we give Bart less than 2/3, then Lisa has a winning strategy. So these are the budget that we are interested in, and we call it the threshold budget. That is the minimum necessary and sufficient budget Bart needs to win from that vertex. And we can compute that budget for each of these vertex in this example, and we'll see that this budget looks like this. 0 means that Bart doesn't need any budget because it's already there in his target vertex, and 1 means that because there is no path from that vertex to his target, even if you give Bart the whole budget, he can't. And if you observe this has a Yeah, so this is what we call threshold budget, and in fact, in continuous bidding game, we can show that the threshold budget always exists. That means this is same as saying that the bidding games are determined. And the definition of threshold budget, there is a slight subtle point here that we say that a budget is a threshold budget if we give so if we say that B is the threshold budget for BART at vertex B. If we give a BART more than B, then BART can win. And if we give budget less than B, then he loses. We don't say anything about what happens if we give exactly. That's the definition of the threshold budget for continuous.
So, Suman, what is this? This TH is some threshold.
So this is the threshold. Yes, threshold.
And
threshold.
okay, and this is the theorem says that such a threshold exists.
Threshold exists. Yeah. There's a continuous bidding, and this has been done in 90s. Sorry, I can't see that, but yeah. Yeah. And
so then one of the vertex has a threshold of 1, right? So that means that
yes,
you said that from the vertex you can't win.
Yeah, you can't win.
And you can't give more than 1 there.
Yeah, you can't. I mean, that's a symbolic, but yes, you are right.
So threshold vertex being 1 means that like that he can't have a budget from which he can win. He can't have a budget more because
yes. I mean, if you can put the 1 in the definition, you will see that. I mean, you can't give someone more than budget 1. So we say that. I mean, it's a symbolic budget circuit. So we say that the threshold budget there is 1. Okay. And you can see that this threshold budget, they satisfy average property, which means that threshold budget at a vertex is average of threshold budget of to neighboring vertex, which we say as V plus and V minus. So not, I mean, there could be many neighbors, but the V plus and V minus are the 2 neighbors which has most budget, most threshold budget, and the least threshold budget. I mean, these are the maximum and minimum vertex with respect to the threshold budget. So we call it max neighbor or min neighbor. So that means that, like, if, I mean, the idea is that if BART wins at a vertex V, then he will always choose to go to V minus because threshold budget there is the minimum. And if Lisa wins, so she will choose V plus because for BART threshold budget there is maximum. So it will make his game difficult. And threshold budget at vertex V is average of these. And from this also, we also get the how much one player has to bid at a vertex. And this is irrespective of whatever budget he has, like budget greater than equals to threshold V. He will always, I mean, his optimal bid is always threshold V plus minus threshold V minus by 2. And we can compute this threshold budget by a simple reduction to a stochastic game, and it's the problem. And computing the threshold budget is in the intersection. So this is about Richmond continuous reachability games, and now I'll go into the discrete counterpart of the bidding games. That's what we did. So first, reachability Richmond discrete bidding games, which was already done. So in the discrete bidding games, we now have total budget, which is also part of the input of the decision problem that we'll consider, which is some integer k. And configuration is now vertex V. I mean, configuration, it was also earlier, it was also like this, vertex V and the budget V1 and V2. And at integer, player I bids at each turn, player I bids an integer small pi, which is within capital P, which is within his or her budget. And if B1 greater than B2, then player 1 moves, otherwise player 2 moves. But you saw, I mean, I did not explicitly probably mention that in continuous bidding, we don't consider tie breaking. That means we don't say what happens if both the players bid exactly the same, because in continuous there are many possibilities of bidding, so we don't necessarily consider tie breaking, or we can arbitrarily choose that, okay, when tie occurs, we will always let player one choose, but choose the, but let them move the token. But for discrete bidding, the tie breaking is crucial because there are not many bits, it's only integers. And depending on what tie breaking mechanism you choose, the theory varies. That means, and there are some tie breaking mechanisms for which these games are not even determined. So for today's talk, I'll fix one tie breaking mechanism, which is the following, which is we call advantage based tie breaking mechanism. That is, we give another resource on top of budget, which we call advantage, which we denote here by the hat. We'll give it to some player in the beginning of the game, and whenever a tie occurs, for example, if suppose both of them are bidding 4, then the player who has the advantage has two choices. Either he can choose to keep the advantage for future and let the other player win. That means that's what happening here. That both of them are bidding 4, but Bart is keeping the advantage for future and let Lisa win. So his budget is increasing because Lisa is choosing the token. Or he can play the advantage, and that means that he wins the bid and choose the token, choose where to move the token, but he has to pass on the advantage in this after this time to the other player, and this goes on. So this is what we call advantage based tie breaking. Whoever hold the advantage can break the tie, however he or she can choose. And the budgets now of the from this 0 star means you have budget 0 with the advantage, and 1, yeah, and so on. And K+1 is a symbolic budget, like 1 in the continuous counterpart. That means that, I mean, so when we say that the threshold budget at this vertex is K+1, that means that you can't, and from that vertex, that player cannot. Okay. So we had just the decision problem, just the initial, but I mean, we ask that whether for a given initial budget part can win or not. And this is, let me just go through the literature a bit for both continuous and discrete. For continuous bidding, I have shown that from 90s, we knew that the threshold budget exists and the average property, and how the optimal bids look like, and computing the threshold budgets for any intersection point P. And in the late 2010, around 29, have the same theorem for the discrete counterpart for the finite duration games for reachability, and an XP time value iteration algorithm. And for infinite duration games, since 2019, I think they have shown, they have reduced the bookie or parity, bookie and parity continuous bidding games to reachability bidding games easily, and it has and they can compute, they have computed the threshold budget. It's a work by Agni and et al. And for infinite duration discrete bidding games, the knowledge was only about the determinacy of Muller games, which is the most general form of infinite duration. Qualitative, of course. And we started from there, and we were we wanted to study, of course, whatever we know for the other part of the games. We wanted to study for infinite duration objectives and discrete bidding games, and we wanted to know that whether threshold budget has some structure there, like the other parts, other bidding games, and if we how efficient we can compute the threshold budgets, and whether they have, and if from the threshold budgets we can see the optimal bids or not. So these were the problem that is the content of the first work, and I'll show first how we solve the bookie games. So bookie winning condition is as follows. So for reachability, you know that you have Bart has a target vertex that he has to reach, and for bookie it's given a target vertex, and he has to reach the target vertex infinity of. For example, here suppose the target vertex is T, so Bart has to visit this T infinity of. So from earlier part, we knew that the games are determined. We knew the Muller games are determined, which is more general than bookie games. So we knew that bookie games are also determined, and from that information, we knew that if we can compute the Lisa's threshold budget, that is a Kobuki threshold budget, then that's same as computing the Bart's or bookie threshold budget. So we didn't know that how the threshold budgets look like, or how to compute it. So I'll show how we compute the threshold budget for Kobuki games. So Kobuki objective means that Lisa wants to make sure that the T is visited only finitely often, right? Because Bart wants to visit T infinitely often. So we construct many small games which are all reachability, special type of reachability games. So we had already knowledge about how to compute the threshold budget in reachability games or safety games. So we'll use that in this fixed point algorithm. So we construct small reachability games. The first reachability games is as follows. So here, Lisa wants to compute the threshold budget so that she can make sure that the game doesn't go to T, which is safety, which is exactly opposite the reachability games. If you know how to compute the threshold budget of the reachability game, you know how to compute the threshold budget for safety games. So this we know, and this will, the threshold budget that we compute in this game, by which Lisa ensures that T is never visited. And in the next step, we'll compute from T. So we have the threshold budget at U and V and W. Now in the next game, those are my what we call target budget. That means we consider another reachability game, and we want to compute a threshold budget at T, given, and we are given some target budget at U, V, W, and we want to compute threshold budget by which Lisa can make sure that if the game goes to say W, then Lisa has at least that much budget that we computed in the earlier game. So this is so visit V minus T with a target budget. These are called frugal reachability games. So in the reachability game, there is no target budget. It's okay. We don't care about how much. We only care about that if you reach the vertex. But this game, frugal reachability game, and target vertex are associated with a budget, and we want a player to visit that vertex with some given budget. But the algorithm is exactly same as it's a adaptation of the whatever algorithm we have for reachability game. So it's not difficult to compute these budgets. And I'm not showing it, but you can believe it. And we can go on. If we then consider another game, which is again a frugal reachability game, and we ask that we compute the threshold budget in UVW so that with this budget, Lisa can ensure that if the game goes to T, then there she has the budget that I computed in the earlier game. And so on. So in some sense that the first threshold budget that I computed, the first game, with that budget, Lisa ensures that T is never visited. The second budget, I ensure that the game starts from T, but she can ensure that the game never visits to T anymore. And in the third game, the budget that we compute is the budget by which Lisa can ensure that the T is visited only once. That is this one, and never again. And we can continue, and we can actually see that these budgets, the threshold budgets that we compute in the left-hand side, for example, these are non-increasing because the objective in the games are becoming easier for Lisa. So you can think of the first game as the target budget at T was K plus 1. I mean, as I said before, if you want to make sure that the game doesn't go to T, you can also pose the same problem as that the target budget at T was K plus 1. In the next game, when this UBW, the target budget at T was less than K plus 1. So the game is becoming easier for Lisa. So that shows, I mean, that kind of intuitively shows you that the threshold budget also at UVW are non-increasing. And because these are all finite, eventually it will reach a fixed point. And in that, with that budget that we compute at the fixed point are the actually budget by which Lisa can ensure that the T is visited only finitely. So by this way, you compute the threshold budget for Kabuki objective, and of course, it will give you also the threshold budget for Kabuki objective. Is it clear?
Here, are the budgets continuous or discrete?
No, these are all discrete. I'm talking about discrete bidding. So that's why these are finite. So we have now, from this algorithm, we get a structure for the threshold budget, because each of the budget that we computed, we get it from the small reachability games. And
So one question. So
Yeah.
are you also able to compute this fixed point?
Yes. I mean,
So
you
it
can run.
can't happen that it keeps increasing.
No, because all these budgets are
Oh, this is
finite.
with integers. Okay.
Yeah.
I see.
Yeah. And this gives and not only it gives a threshold budget, it also gives that the information that the threshold budget satisfies the average property, because it satisfies the average property in each small games. So it will continue satisfying the average property. And we also get what the optimal bids for the Buki or Kabuki game from the small. But in these games is exponential in K, because K, the total budget, is encoded in binary, and it can go still exponential in the encoding of K. So that so we can call it pseudo polynomial. So we also, I mean, we are still looking for some better algorithm for these Buki games. But we move on to parity games, which are generalization of Buki games, in the sense that so we have the game graph, and each vertex is now associated with some priorities, and BART wins if and only if that infinitely occurring max priority is odd. And for parity games also, we have a fixed point algorithm that we had, like we had Buki games. We had an extra induction of our priorities, but that kind of expected. But but anyway, so for parity games also, we get the same that we had for Buki games, that it's the threshold budget satisfies the average property. We know how to compute it, and they satisfy the average property, and we know how the bids look like. So from this, we will, using these two information, in the next, I will show an NP procedure for parity games that will give us and like for both BART and Lisa, because parity games are symmetric. So we'll give that will give us that parity games are in NP intersection. So what is the procedure? So we want to compute the threshold budget, right? And we know that the threshold budget satisfies the average property. So we guess the threshold budget for each vertex, and we check. So the average property in discrete, I have not explicitly mentioned, but it's a slight different from what the normal average in the continuous, because these are I mean, these are integers. We have to adjust anything, but it's still, we can call it an average. It looks like an. So we'll first guess function T that we candidate for the threshold budget, and we'll check whether they satisfy the average property. If it fails, we know that it's not a good guess. So if it passes, then we construct a game GT, which depends on T, which is a turn-based parity game. We are trying to solve. We are trying to show that that the bidding parity games are in NP intersection point, and for that we construct a turn-based parity games, GT of size poly, actually linear in G, and there we establish that TV is winning for player one, for Bart in G, if and only if Bart wins from every vertex in GT. And that once we establish that, because it's only poly in GT, we can actually guess winning strategy in that game. And if there is one, then we say that the T is a right candidate. So that's the one direction of the procedure, and we can do that from Lisa's perspective, and that will give us NP intersection. So I'm not exactly showing, going through in details that why this, and this is the crucial point, but I probably won't have time to exactly show why this is linear, or but if you are interested, I can come back to that. And this was the content of what Informatics Statistics 2022. And this is the first part where we considered the computing threshold budget in parity discrete bidding games, and we showed it that it is an NP discrete OMP. So we all know that we showed that the polynomial size winning strategy exists. Not shown in the slides, but it's there. And we improved the earlier known, and we only knew X-prime algorithm, and now, I mean, even for reachability, we can still use this algorithm for reachability. We'll have an NP intersection. So turn-based parity games, so we have shown it in NP. So turn-based parity games are, we know that it's NP intersection point P, but not known to be P. We now have a quasi-polytime algorithm. But turn-based parity games actually can be reduced to discrete parity game for a fixed budget. And in this work, we have shown that the discrete bidding parity games are also in NP intersection point P. So it's seemingly harder than turn-based parity game because we don't have a reduction on the opposite side, but we still have the same complexity class. And this is, I don't know, and we can think about it that if there is actually a gap on. And this is, and from here we move on to the next part of my talk today, which is an application that we propose of continuous bidding games, which was in the introduction part before we delved into discrete bidding games, in application in decentralized synthesis, multi-objective decentralized synthesis. So I'll first
Suman, in the first part, just a question in the first part, this thing of when a player pays the money, it goes to the other player. Is that realistic? I mean, I was thinking maybe it's more practical that, you know, I mean, something like the IPL auctions and, you know, maybe the money goes to someone else, not to the other, you know, the other bidder.
Yes. I mean, so there are these all pay bidding games that have also been studied for that. I mean, this is we studied it from a theoretical point of view, but you are right that it can be argued that the mechanism where higher bidder pays to some other bank, for example, or whoever is auction, that's more intuitive in some scenarios. But yeah, that's what I have to say. But usually, like if you study those all pay bidding games, then that might not be totally fit in the context of infinite duration, because here the budget remains fixed throughout. So, so that kind of one incentive, if we look in, if we want to study from the verification community, I don't know what the resources will look like. So this is what, and this is what I am going to show possibly in the sense that where it can be applied, but we'll have to think about what kind of resource we talk about. But keeping the budget constant is an incentive for an infinite duration version. So I'll first introduce what multi-objective control problem is. So suppose you have office, for example, and there are trash cans around in some places in your office, and you have a robot that that clear those trash cans. But the robot also needs to get charged in time to time, and the objective is that the robot should repeatedly empty the trash can, and whenever it needs whenever the battery is low, it should recharge. So this is the second objective. And so sorry, skipping the animation this moment. And typically we can and we want to synthesize a controller for this robot given a scenario. So typically, this is the framework that we have also mentioned earlier, that you have a system. We want to synthesize a controller for a given. So there are, say, two objectives. We can also, of course, take conjunction of these two objectives, and we can synthesize. We can see whether a controller exists for this specification. And this is typically called centralized synthesis, like centralized controller synthesis. But we want to approach the same problem, synthesizing this controller for these two objectives in a slightly different way, which is we want to synthesize the two controller for two objectives independently, and we want to have a scheduling mechanism such that these two controller can be scheduled and gives a whatever it needs to, and can tell the system whatever it needs to do whenever it gets an input from the environment. This is a new framework that we are interested in, and we propose bidding games for the scheduler. Of course, that should be clear from the theme of the talk. And why? I mean, I'll show why would you consider schedule why this framework is interesting, and why bidding games is a solution for is a fair solution for the scheduling mechanism. So let's see how this composition works. So suppose the trash can is now full there in the corner, right corner. And now of course, when we talk about two controller, we are introducing two players. For example, in this context, let's say Homer and Marge. And now Homer is controlling the robot, and he goes to near the trash can. And whenever a new trash can arrives in the left corner with trash, he will go there to collect the trash. And you could see that the status of the battery also changing as he moves around. And at some point, the scenario is as following: there is a trash can which is full, and the battery is too low. But the Homer's objective was only to collect the trash can. He doesn't suppose he doesn't care about the battery at all. And Lisa's objective was to Marge's objective was to make sure that whenever the battery runs out, the robot goes to the charger. So here she will take the control from Homer and moves the robot to the charging point. And whenever the charge is enough again, she will give the control to Homer, and he will collect the trash. So this is what we want. We want two controller which will only care about their own objective, but we want somehow we want to compose them together so that at the end both objectives are satisfied, because these are not these are two overlapping objectives in the sense that both of them actually can be satisfied, unlike say zero-sum version. So this is what we are interested in. And here we are saying that two controller are actually two bidding strategies, and the scheduler is the bidding mechanism. And we are saying that this gives somewhat fairness, because bid values represent the scheduling agency. And more importantly, what we believe that this gives you a modularity in synthesizing the controller, in the sense that if one objective changes in some sense, if suppose you place the trash can in other places, not the one that is there, then we don't want to synthesize a new controller for the other objective, which is for recharging battery. And if we approach this problem with the centralized controller, that we had to recompute it again if one objective changes, we are claiming that if we approach the problem in this decentralized manner, then it gives us some modularity, in the sense that we don't need to recompute the one controller if objective of the other controller changes. And let's see an example here. So suppose there is a graph, and for simplicity, I'm showing a finite duration game. So Homer just wants to visit these three vertices, and Marge wants to visit the vertices where she can charge the battery. And so how do we approach this scheduling is that Homer, as I said, he doesn't care about the battery. So he will he doesn't know that where the battery is. He only cares about his objective, and he will approach the game as if it's his game, and he can actually we know that if we give Homer more than 1/4 of the budget, he can make sure that the robot visits one of these three vertices. Similarly, Marge, who only cares about that the battery gets charged in time, she doesn't know about the other objective. So if we give Marge a budget more than half, we know that Marge can satisfy her objective. So you can say that the sum of these two budget is less than 1, and this is an ideal situation to compose them. That means that if we let them play whatever their winning bidding strategy in their individual game together with each other, then actually at the end the both of them objective will be satisfied. And this is not always the case, but in this example that is the case. That is, we'll distribute the total budget, because the budget required for them is total budget required for them is less than 1. We can actually distribute the total budget in some way. Say we are giving Homer 1/4 plus epsilon and giving Marge 3/4 minus epsilon, so that epsilon is greater than half, I think. I don't see the point. And we let them play the bidding strategy from their individual bidding game, and we are just composing these two. And what happens is that Homer bids 1/4 and Lisa bids 0, and Homer wins the bid there, and he moves the robot in this left vertex. And from there, actually, he doesn't care that winning the bidding here, because both of them, like even if he loses, if his adversary chooses the next vertex, he also wins in his objective. So he doesn't care. And for Lisa, it's important because Lisa has to win. Sorry, not Lisa. Marge has to win the bid here, because if she doesn't win, then her possible adversary can move the token to the other vertex. So in fact, the condition of epsilon actually makes 1 minus epsilon greater than epsilon, and so Marge wins the bid and moves and in fact can move the robot in her target vertex. So we saw that if we compose this two winning bidding strategy, if the total budget required is less than 1, then we can compose them. We can synthesize these two controller strategy independently and compose them together, and still get a situation where both of the objectives are satisfied. And this is what we called strong synthesis, in the sense the other player doesn't care about one player doesn't care about what the other player's objective is. But
so Suman, what am I missing? So I mean, it looks like these are contradictory, right? If this guy has more than 1/4, I mean, if you give them 1/4, I mean, and little more than 1/4 and little less than 3/4 to Lisa,
Yes. Yes.
then I mean, how can they both fulfill their objectives?
Yeah, no, so 3/4 minus, so that's the condition I don't see actually. So epsilon, the condition of epsilon was it's less than half, right? Yeah. So March requires the budget to be more than half, and because this epsilon is less than half, even the 3/4 minus epsilon is actually more than half. So we are saying that with that budget, she can win against any adversary. She doesn't know that what that adversary she is playing against. And we on the other hand, we are saying that
they can, in principle, they can both win.
Yeah, they can both win.
Okay,
And
it's
because
not
it's not contradicted. But this will not be always the case, because I mean, in some other situation, the sum might be more than one, and for that we have to deal this problem differently.
Okay, but so it can't be the case that the strategy that let's say Homer has prevents March from visiting her objective.
No,
that can't happen.
That can't happen. So that's that is the crucial point here. That I mean, Homer kind of because Homer kind of win against any adversary, she also against March. So March is one possible adversary, right? So of course March cannot prevent Homer to win for his objective. That is the scenario here. But yeah. So this is an example where
How is the budget? Who decides the budget of Homer and March, both of them?
So we consider the two separate bidding games, one for Homer and one for March. I had shown it here. So for example, so we consider for Homer, this is his bidding game. So you compute the threshold budget in this game for Homer. So here the objective is to visit these three vertices, and we compute for March the threshold budget from this bidding game, where her objective is to visit these two vertices. And we see that whether this threshold budget that we computed in these two bidding games, whether the sum of their threshold budget is less than 1 or not. If it is less than 1, then we are claiming that we can compose these two bidding strategies. If it is not less than 1, then we cannot directly compute them. And we deal that problem differently. Is it clear?
At one point of time, you said that the budget indicates the urgency of both Homer and right?
Yes.
So
not
both
budget,
can be
the
dependent on one. Bids indicate the urgency of both the players.
Yes.
So it can be so that the bids, both of their bids are interdependent. Right? Like a trash can be near to a charging point. Like at the same point, there can be two trash cans which are filled, and one trash can might be near to a charging point, and the vehicle might have enough battery to go to the trash can which is near the charging point and then go for charging. So both can be dependent on one another also, right?
Yes. I mean, so typically what Marge sees, she doesn't see the charging, the trash can. She only sees that what the current battery status is and where the recharge stations are, right? So she will try. So her urgency will only depend on that, and Homer's urgency will only depend on that where the trash cans are and whether they are filled or not. Now, if we can compose, we cannot always compose, but if we can compose, then actually, suppose a scenario where the battery is very low, then actually Marge can take the control with their bid. She is like bidding against a complete adversary, so she will. That seems like automatic, but that is what these bidding mechanisms guarantees, that you can always make sure that you bid according to your scheduling urgency. Your scheduling urgency is coming from your objective. That it means that if the battery is slow, then it's urgent for me to bid. She doesn't care whether there are trash cans which are also filled or not. It's urgent, so she bids enough so that she can take back the control. But if we compute the threshold budget separately, and if we see that the sum is less than 1, then that automatically guarantees that by that scheduling, I mean, by the bidding policy from the scheduling urgency that they are getting, if we compose these two, then both of the objectives will be satisfied. So that's what these bidding games are guaranteeing. Is it?
So for merge, like suppose there are two charging points, then both the charging points are equally important for merge. There's no difference.
Yeah,
in the
no, there is no
charging
difference between the charging points. See, our objective is to visit either of the charging points.
Okay.
And so here is one example where I cannot compose them as I composed it early, as we composed it earlier. Is that here?
Suman, just to give you a track of the time,
Yeah.
we should finish in like 5 minutes.
Yeah, I'll finish it in 5 minutes. Yeah. So here, Homer wants to visit, say, this trash can, and Marge wants to visit this battery recharge station. If we compute the threshold budget in the way we computed, including the other players' objective, then we'll see that Homer's objective is 7/8. I mean, he needs more than 7/8 to budget to visit this trash can, and Marge needs more than 1/8. But because the sum of this is becoming greater than 1, we cannot just compose their bidding strategies blindly. But so what is the solution in this case? And here the strong synthesis fails. So we can't, we have to assume something, like one player has to assume some behavior about the other player. So what is the assumption we can, that can guarantee that we can compose them? The assumption is that if you see this, I mean, I can't, sorry, I can't use the pointer, but I mean, I have the pointer. If the vertex that is, Homer knows that the Marge wouldn't take the edge. So if the robot is there, the left penultimate vertex, then Homer knows that. So the assumption is that we are letting them know that, okay, you can't play play blindly, but I am letting Homer knows that, okay, this is Marge's objective. Marge wants to visit this vertex. And we are also letting Marge know that this is Homer's objective. So once we are giving them this information, and we are also telling them that the other player is playing for their objective only and not to defeat you, then when the game reaches in this vertex, the left penultimate vertex, then Homer knows that Marge will not choose to go down, because he knows that her objective is to visit this vertex where there is an energy state. Similarly, Marge also knows that Homer will not choose to go down because his objective is to take the right edge. So if they didn't know this information, then both of them wanted to would have tried to win the bidding here, because if they lose the bidding here, a complete adversary will, I mean, they will defeat them, right? But because they now know this information, they will not bidding anything in that vertex. In the sense, they will not care whether they win the bidding or not, because they know that even if I lose, the other player will not choose something that is defeating for me. So that, because this is the case here, we can remove this kind of vertex from the game, and we can recompute the threshold budget, and that if that turns out to be less than 1, we will say that, okay, if we let them know this amount of information to this player, that the information being the other player's objective and the rationality behavior, then we can decompose their bidding strategies and we can so that both of their objective will be satisfied. So this is what's called assume admissible synthesis. We are synthesizing, assuming the admissible behavior for the other player. And so this is the
How
typical
to find such vertices? How to find such vertices?
yeah, that is, and that's what we study in this paper, how to find such vertices. This is what we called non sorry, the word redundant, removing redundant vertices from the graph, and then we again compute the threshold budget, and we see that whether the sum of the threshold budget is less than 1. So there is a characterization of the redundant vertices, but I have just shown one example to show that how we approach this kind of this problem. So I mean, in these two examples, what I wanted to convey is that we are trying to study this problem where we have given a graph arena and a two non-conflicting objective, and we want to synthesize two controllers and so schedule them via bidding so that they fulfill their own objective and own objective. And these two controllers, if we fail to synthesize it to independent controller, we let them know some information, and we see that whether it can be synthesized or not. So this gives us a spectrum of synthesis. First one being strong synthesis, and the second that I explained was assume admissible, and subsequently assume guarantee, which I have not yet talked about. And this is, I mean, of course, once you are giving some information, you lose some modularity because you cannot now compose with any other synthesize. I mean, you are the controller, and the controller needs to know that this is the information you now need to share. So you lose some modularity, but you increase the solution space. And we in this paper we characterize the arena and the graph so that, I mean, one or the either approach can be done. Of course, there will be scenario where all of them fails and we don't know how to deal with them, and these are not complete algorithms in that sense. And this is the work that will be presenting in the class. So this is the takeaway from the part 2, that we are studying decentralized synthesis problem and studying a spectrum of synthesis mechanism, and we are studying for qualitative objective only now as of yet, and the future work will be studying this for quantitative objective. And I mean, even though I said it multiplayer, and of course I have only shown 2-player because the theory of bidding games as of now we are developed for 2-player. So it will be interesting to know what multiplayer, how to deal with the decentralized problem for multiplayer, multi-objective, like more than 2 objectives. And that's all. Thanks. If you have any questions.
Thank you. Thank you, Suman. Very nice talk. Any questions? So we had several questions during the talk. So maybe one quick question. And anyone else? I'll give a couple of seconds. If not, I'll ask them. Yeah, so just a technical question about the first part, the bidding. So if I mean, yeah, you don't have to change slides. Like,
Okay.
So, I mean, I'm just curious, if you assume the budget is some small number, like say 2 or 3 or something like that,
Yeah.
do we understand the complexity better?
The fixed budget.
Just to understand, like, I mean, if my K is 2,
Yeah.
okay, and if we're talking about discrete bidding.
Yeah.
Okay.
So then it's like if you are, so you're saying that for fixed budget, what is the complexity? So that is then it's polynomial, right? Because
I see,
the
I see,
exponential
because
factor is the encoding of the budget.
I see. Any other questions? Okay, great. So thank you so much,
Thank you.
Suman, for the talk.